Kristen Atchison here, and we're talking about, we're continuing our discussion of threats to internal validity and null effects. So this is the slide that I showed in class. Previously, we've discussed design confounds, selection effect, and order effects, and those were in previous chapters. We kind of touched on them in class, but again, we had previously covered those. Yeah, in class, we discussed the 6 major threats to internal validity, and again, 5 of these threats can be solved or controlled for by just adding that comparison group. So remember, maturation is just kind of that we normally change over time, and then in that pre-post test one group design, maybe that's what's causing our change. History is some other outside effect happened concurrently with the treatment, and maybe that caused the effect. Regression to the mean is just the idea that if you have an extreme score, it's not likely to stay extreme. It's likely to go back towards the mean. Usually extreme scores are caused by kind of chance factors, and those chance factors are not likely to happen again. So again, those scores tend to be more towards the middle. Attrition is dropout. Remember, we can have mechanical subject loss where people aren't included in the data set because of some sort of error in the data collection. And these are, again, chance factors and are not normally something that we're worried about. But we can also have selective subject loss, which is one that we're concerned about. That usually has something about the person causes them to drop out. And this is especially problematic when it's related to either the independent or the dependent variable. Testing is just the idea that we change with subsequent testing. So you get better at taking the test. You get bored by taking the test. There again is some change there, and this again is a threat to internal validity. And the last one is instrumentation, that the instrument changes. Maybe your observers just get better at noticing that behavior. And so again, that this could explain the difference between pre-test and post-test. And again, by adding that comparison group, maturation, history, regression to the mean, testing, and instrumentation are all controlled for. Attrition, you just kind of watch your data very closely. You can also do kind of a match design, different things like that. To really count for those attrition changes. So the last threats to internal validity that we're going to discuss in this video lecture are observer bias, demand characteristics, and placebo effects. So experimenter effects or observer bias are these potential biases that occur when the experimenter's expectancies change their behavior, change and influence the outcome. Some of it changes their behavior in coding it changes their behavior towards the participant, these sorts of things. And we can control this by keeping experimenters and observers blind or unaware of the expected results. So when I was collecting my dissertation data, clearly I had a vested interest in it, and I really wanted my hypothesis to be supported. And I was collecting the majority of the data. And so it mattered if I knew what conditions infants were in, if I knew whether they were in test trials versus control trials. So we kept me blind. I did not set up the computer. I did not fill out any of the paperwork. We had another student do that. We literally covered the side of the screen that had the stimuli on it for the infants. So I was literally blind to that. I couldn't see any of that. And we also, wore headphones, so I couldn't hear anything either. Often I was so kind of in my zone, coding this infant looking behavior that I didn't even realize when this experiment would end, and I wouldn't have even noticed. So again, by keeping the experimenter blind, we can control for observer bias. And again, this can be kind of any kind of behavior changes. And a lot of times it's not an overt, oh, I'm going to do this so that my hypothesis. I mean, clearly I would have never done that. But there's all these kind of subtle kinds of situations. Or when you are in an ambiguous call, is this behavior or is it not? If you know which condition the child's in or which condition the participant's in, it's going to be more likely that in an ambiguous situation that you might side towards the thing that you want, whether it be consciously or unconsciously. So again, by keeping the experimenters and the observers blind, It really controls for that. Another example is when I was an undergraduate, in the lab that I worked in Texas A&M, the people that actually did the observing, the people that actually did the data collection, were actually the newest students. They were the students that were newest to the lab. They were undergraduates. It was usually their first semester in the lab. And nobody told them anything. They told them how to look, what to look for behaviors, but they had no idea even sometimes what the studies were looking at, what they were interested in. They had no idea what conditions infants were in. And they were never included in any of the lab meetings that talked about hypotheses and these sorts of things. They really were blind. And the longer they were in the lab, if they were kind of in their 2 semesters, chances are they had to move up out of observer because they started to kind of figure stuff out, and we wanted to really keep them blind. We filled out paperwork when they weren't in the room. We talked about things when they weren't in the room related to the experiment. So again, that they really were completely unaware about what we were even interested in looking at. And again, these are different ways to keep your observers blind, to keep your experimenters blind, to control for changes in behavior. The next one we're going to talk about is demand characteristics. Demand characteristics is when the participant, so observer bias and experimenter effects are about the experimenter observer. Demand characteristics are about the participant. The participant guesses what the study's about, and they modify their behavior because of it. These are they will cue the participant in how to guide their behavior. So another example from when I was an undergrad, just like every other psych undergrad, I had to do psych studies. I had to participate in psych studies for credit for my intro psych class. And I had read the textbook the night before going to this study, and it just happened to be on a similar thing than that was in the textbook. So I was kind of primed to what was going on. And I remember sitting there in this big lecture hall where they were doing this and going, oh my gosh, this is what I was reading about last night. This is that. And so I even on my thing wrote a note, like I read about this in the textbook last night, so that they knew that I was more aware of what they were doing, and that could compromise their data. I was letting them know that demand characteristics were at play, because it's very hard to not change your behavior. And so again, knowing anything about the study participants can modify their behavior. That's a lot of times why you'll have things like debriefings where you don't tell participants about things until after the study is done. We even did that with our infant participants. The infants clearly weren't going to modify their behavior. We didn't even want our parents that were holding the infants to know kind of what we were looking at, what we were expecting. We'd tell them what they were going to see and what they were going to hear, but not what we were testing, not kind of our hypothesis, not any of that, because we didn't want parents to modify their behavior and infants pick up on that. So again, demand characteristics, the way we control for those is we really need to make sure that the participants stay blind to the outcome, the ideas, the research questions, and the hypotheses of the studies. The third one we're going to talk about is placebo control and double-blind studies. And these are other ways that we can control for both experimenter effects or observer bias and demand characteristics. So clearly, the kind of gold standard of examples is in a drug treatment. Demand characteristics suggest that participants will improve as a result of the drug, okay? So you have a headache, you take a Tylenol, and almost immediately you start feeling better. That Tylenol hasn't started working yet. That's a placebo. You think it's going to make you feel better, and so it does. It's the same way, a little kid with a Band-Aid. They have this tiny little cut. My daughter does it all the time. It has this tiny little cut. It hurts so bad. I can't, Mommy. I can't handle it. And you put a Band-Aid on it, and all of a sudden it's miraculously better. Again, that's kind of the effect of a placebo. The participants expect to improve, and the expectations cause the improvement, not the drug, not the Band-Aid, not whatever that other thing is. It's that expectation that's changing or causing the improvement, not the drug. So a placebo control group is used to assess whether participants' expectancies contribute to the outcome of an experiment. And typically in a drug study or something like that, they'll be given a sugar pill where the pill looks very, very similar to the treatment medication. So again, they won't be any way to tell if they're getting the actual medication or not. You'll see that in other treatment studies as well. So when you have some kind of treatment group, you won't compare them to a group that did nothing. You'll typically still compare them to a group that did something. And the key part of this is that the participants have to believe that they're receiving an effective treatment. To really measure the effect of their expectations, they're going to again have to think that they're getting a treatment. That could be the inert substance of a sugar pill. It could be, again, some other kind of pseudo treatment, but that's not the actual treatment that's being tested, something like that. They have to expect there to be an improvement. They have to expect there to be a change for us to be able to use placebos to measure those expectations. If the participants who receive the actual treatment or drug improve more than those that receive the placebo, then we have a lot more evidence, a lot more confidence that it was the drug or the treatment that produce those beneficial outcomes, not just the expectations of feeling better. Another way we can do this to really control for both, so placebo controls will really control for some of those demand characteristics, and a double-blind experiment will both do the demand characteristics and the experimenter effects. So both, in this procedure, both the participant and the experimenters are blind to the conditions being administered. So the people who are actually administering the treatment don't know if they're giving the participant the treatment or not. And so again, and the people that do know aren't having any interaction with the participants at all. So that again, nobody knows what's going in the interaction between the participant and experimenter. Neither one of the parties knows what conditions are being studied. And again, this controls for both the demand characteristics that you could see with the placebo, and it also controls for those experimenter or observer bias. And it really allows us to rule out both demand characteristics and experimenter effects as alternative explanations for the study's outcome. This is really helpful because then again, it improves our internal validity. We can say, no, it's not demand characteristics that's caused the change. No, it's not experimenter effects that have caused the change, because we've controlled for those things. So we've ruled out more alternative explanations, which again improves our internal validity. That wraps up the threats to internal validity. We're going to move on now to the second part of this chapter, interrogating null effects. So what if the independent variable doesn't make a difference? We've spent all this time talking about, okay, so the independent variable did make a difference, but was it really our independent variable, or were there these threats to internal validity? Are there these alternative explanations as to what's going on other than the independent variable caused change in the dependent variable? But what if we don't find any change? What if there's not any change in the dependent variable? What if we can't reject the null? What if our p-value is not less than 0.05? There's three different things that can be going on in those situations. And some of it comes down to that signal to noise ratio that we talked about in class. So one of the things is perhaps there's not enough between group difference, okay? Perhaps there's not enough signal. Perhaps the two groups aren't different enough. A second thing that could be going on is perhaps there is too much within group variability and we can't see the differences, okay? So perhaps there's too much noise. Perhaps there's too much noise variability, and so other variability, so we can't see the differences that the independent variable may have caused. And the third thing is the one that everybody forgets. Maybe there really was no difference to begin with. So perhaps the independent variable does not cause change on the dependent variable. So any of these three things can be going on. And we don't necessarily know which one of the three it is. If we fail to reject the null, we don't know that it's between group variability, within group variability, or no difference. We don't have that information. Null effects can be hard to find, okay? To really find that there is no difference, those can be difficult to figure that out. So again, there's the 3 different causes. Perhaps there's not enough signal. There's not enough difference between our groups. And this can be caused by several different issues as well. One of which is ineffective manipulation, okay? So maybe the thing we manipulated, we didn't manipulate it right. And so that's why we don't have a difference. Another option is insensitive measures on our dependent variable. So ineffective manipulation is about our independent variable. Insensitive measures is about our dependent variable. Maybe we didn't do a good job measuring, and it's not sensitive enough. We can't see the differences because we didn't do a good job measuring. Another one that we're going to talk about is ceiling or floor effects, and I've got some graphs that'll explain that as well. In terms of too much variability within groups, we could just have a measurement error. Okay, so again, too much noise that we can't see the signal. It could just be that somewhere we wrote down a number wrong, okay? And so we have this variability in the group that's not actually there. There could be due to individual differences. And this is, again, why our within groups designs are more sensitive than our between groups designs, is because they're really going to minimize our within group variability. And so individual differences between groups in a between subjects design can cause too much variability within the groups, not make the experiment sensitive enough to detect any change the independent variable may have caused. Other kind of variability noise, and again, this is all that kind of error noise, that it's just everything else. This isn't individual differences. This is just other differences that are in your data. But there may be too much of it to see an effect of your independent variable. And again, our third one, maybe the independent variable doesn't affect the dependent variable. Maybe nothing is going on. Independent variable doesn't cause change on our dependent variable. Now we're going to go in and spend some more time talking about each of these. So in terms of not enough difference between the groups, we can have a weak manipulation. We could have not manipulated our independent variable well. One way that we can check this is to use a manipulation check. Remember, we can see, did our manipulation work? We talked about these earlier. So if you're trying to manipulate someone's mood, ask them after the study, did we manipulate your mood? What was your mood? So that we can see if that manipulation is in fact working. If needed, we can rerun the study with a stronger manipulation. So we tried to manipulate somebody's mood using different kinds of images, and that didn't work. We did a manipulation check, and that didn't work. So we're going to do it again, but this time we're going to do something different to manipulate the mood. Another option is insensitive measures. Again, maybe we didn't measure well. Maybe we're using a 3-point Likert scale, and maybe we really need to be using a 7 or a 10 group Likert, a 7 or a 9 group Likert scale. A more refined scale that can see those nuances and can see the differences between those better. And the third one is ceiling and floor effects. And this happens when your data either clusters up towards the ceiling, so the top. So if I gave a test and everybody was getting a 99, I'm going to have a ceiling effect. Okay, if I give a test and everybody's getting a 32 or is well below 50, I probably have a floor effect. And the ceiling effect on a test would mean that my test was too easy. A floor effect on an exam would mean that my test is too hard. And so again, we need to use a different measure that allows for variability in that data so that we can see these group differences. And again, we can use a manipulation check to make sure that we really are having the variability that we need. So a little bit more on ceiling and floor effects. Again, sometimes these effects can be statistically significant by mistake, or sometimes we can have a null effect by mistake. And this again occurs when the mean for one or more conditions reach on average near either the highest possible score or the lowest possible score. Again, we're all clustered towards the top, we're all clustered towards the bottom. When we have a ceiling or floor effect, we can't tell if we can't interpret the effect the independent variable had on the dependent variable because there's not enough variability between groups to look. So here's an example from your textbook. Again, if you're taking a test and we have the percent correct, if the problems are too easy and everybody's getting them right and we're clustered towards the top, the ceiling, we have a floor effect. And if I'm trying to determine if one teaching method is better than another teaching method, I'm not going to be able to tell because again, everybody's scoring up there at the top. I don't have enough variability in my measurement in my test to see if there's a difference between the two testing methods, or in this case, in the graph between females and males. The same thing with a floor effect. Everybody's clustered down below the bottom here. So here we're lower than 20%. Really dire floor effects for a test. The problems are too hard. You just can't answer them. I definitely took a class as an undergraduate that was like that, where his tests had floor effects. Luckily, he kind of realized it after the fact. And so he curved everybody's final grades quite dramatically because everybody was just failing his tests across the board. The problems were too hard. We couldn't answer them. He was asking us to know things that really, and about so many things that really wasn't possible in the time period and the way he was asking those questions. So again, when we have this, you notice in both of these situations, the pink and the blue lines are right there next to each other, okay? There's not enough difference between the groups to be able to tell. So we're gonna have a null effect in both of these situations, either the floor or the ceiling effect. But the problem is we don't know if it really was that our independent variable didn't cause change on our dependent variable or an issue with ceiling and floor effects, okay? And so in this situation, we need to go back. We'd need to adjust the measurement, adjust the test so that we really are getting an average that's around, without the testing, the differences in males or females. We'd really want, again, exam grades are typically we want them around 75. So in there, and then we can see if this other teaching method really can make a difference. They need to adjust the measurement in this situation so that they can see the variability between groups. Again, another issue that we can have is that there's the within group variability, or the noise obscured the signal, or the noise hid our effect of our independent variable on our dependent variable. And so both of these graphs show the same thing. If you look, there's the one on the left has a lot of variability in that data. Both the dot graph and the bar graph are actually showing the same data. Remember, error bars kind of tell you the standard error in that data. So it gives you descriptive statistics on a graph. And what you see here is there's those standard error bars almost completely overlap each other. While they have different means, again, those standard errors are almost completely overlapping. And the same thing below, if the dots, we see, again, there's only, looks like 2 dots that aren't overlapping. There's one pink dot at the top and one blue dot at the bottom. The rest of them are completely overlapping. While we have different means, there's too much variability in that data to see the difference. On B, on the right, we have the same means, but we have less variability. We have less overlap between those standard error bars. We have less overlap between the dots. And so we have more of a chance of, with that exact same mean, being able to see the differences between groups, okay? So on the left, the variability, all that similarity between how much more those dots are spread out, that variability, all that noise is obscuring any difference. Where on the right, we can see that difference better because there's less variability, there's less noise. And again, think back to that signal to noise ratio, which is what your t-tests from 3510 were, where you have the effect on the measurement of the effect on the top and the measurement of the variability due to chance on the bottom, okay, of that ratio. And the problem is if you have too big of a number at the bottom, then you have to have a really, really huge number at the top to be able to get something that's statistically significant, okay? And here we have on the left, we have too big of a number at the bottom for this difference on the top, the signal, to be able to be seen. Again, we can also have unsystematic variability. So we can have problems with our measurement. We need to use a more precise measure. We need to measure more often. All of these things can help. Individual differences. If this is the variability that you think is obscuring your main effect, your effect of your independent variable, one thing you can do in a between subjects design is you use more people. Remember, the more people we use, the more that sample becomes closer to the population, to the distribution of the population, the less it's affected by outliers, and then the less it's affected by variability. It becomes less variable the more people you collect. And so by collecting more people, we can really kind of start to mitigate the effects of individual differences. Another thing we can do is use a match design. Again, this allows us to match on some sort of variable that's related to what we're interested in. Maybe it's IQ, maybe it's age. Again, it's related to what we're interested in. We did height in terms of our cracker study, our goldfish cracker study. Again, using a match design will really reduce the variability within group on that thing you matched on the matching variable. It will reduce that variability because you'll have the same in each group, okay? And that really will make it easier to see any difference of the independent variable. And clearly the easiest option would just be to use a repeated measures design, because then we don't have to worry about individual differences at all. They're completely eliminated from our study. So again, but again, research methods designs, repeated measures designs are not always possible. So that's not always an option, but that's one way that we can really kind of mitigate this whole issue of individual differences at all that might be contributing to a null effect. The final thing that could be giving us a null effect because of within groups variability is situation noise. And that's, again, kind of everything else, okay? That's the environment, that's kind of everything else. And so we really need to use a more controlled environment to really allow us to minimize the situation noise. Again, we would either balance any differences between conditions, or we would ideally hold them constant. Both of these are control methods to control the environment, but if left uncontrolled, that can contribute to this situation noise, and we can end up with a null effect because it gives us too much variability within our groups. So this is the image from your book that talks about power and effect size. If you remember effect size from 3510, remember it's a measure of effect independent of kind of the size of the sample, okay? And so when you have, and power, remember, was our ability to find an effect when it's actually there, okay? So again, the analogy from your book is when you have a study that has very low power, you can only find large effects, okay? So if you have a candle, a study with low power, and you go into a dark room, you can only find big things. You can only find that Vermont 6-foot teddy bear. You can only find a pillow. You can only find a stuffed animal. You can only find large things with a small amount of power, with a small amount of light. However, if you go into that same kind of dark room with a mag light or some kind of bright light with some kind of high power study, you can find even really small effect sizes. Okay, and again, why we're even talking about power and effect sizes is because you're less likely to have null effects. So if you're looking for that earring with that candle, you're gonna probably end up with a null effect, okay? And then the question is it too much within group variability? Is it too much, not enough between group variability, or was there really no effect? Well, if it's a small effect size, chances are there is an effect, we just didn't have enough power. And the question is, do we not have enough power because of sample size? Do we not have enough power because of insensitive measures? These different kinds of things, okay? So again, it's important to think through these null effects, that there's, when you reject the null, when you fail to reject the null, when you don't find an effect, in our factorial designs, when there is no main effect, why is there no main effect? Okay, why is this happening? Is it because there's not enough difference between our groups? Is it because there's too much variability in our data? Or is it there's really not an effect at all? To kind of hammer home this issues with power and effect size, I wanted to remind you of kind of type 1 and type 2 errors, right? So remember, a type 1 error is that false positive. So you go to the doctor, you're male, he tells you you're pregnant. That's a type 1 error. That's a positive, that's untrue, okay? You got a positive test, that's untrue. A false positive. A type 2 error is a false negative, okay? So you go to the doctor, you're female, you're 8 months pregnant, and they say, oh, you're not pregnant. Well, clearly you are. You got a negative when there wasn't there. And how this relates to power and effect size is we really have a lot of say in how much power we have by setting our critical value, that 0.05. We started this discussion of null effects with that p-value of 0.05. And again, by setting that, we really dictate a lot of other information. So we've seen this before. The real situation, we don't know. We don't know if the null hypothesis is really true or the research hypothesis is really true. We can't know that. We're making decisions based on probability. So when we reject the null, but the null hypothesis is actually true, we've made a type 1 error, okay? And that has, again, a probability of alpha. And we set that. That's up to us. When we set that 0.05 or that 0.01, we're setting alpha. We're setting that probability. What that in turn does is it will set our beta, which is the situation that we have when we fail to reject the null and the research hypothesis is actually true. So by setting our alpha, that dictates our beta. And I'll show you how this works on the graph in a second. By setting our beta, because the probability of power is 1 minus beta, that dictates our power. So by setting our alpha in various levels, depending on the effect size of the distribution, we see different things. So here's kind of how this works, okay? So we set alpha, okay? So when we're doing this, we're always comparing, when we're making a decision, what we're doing is we're comparing, doing it to a comparison distribution in the population. And that's everything under here, under this yellow. And remember, we're setting alpha, and we're gonna set alpha on that yellow curve. Where our actual data is happening is in this distribution of means. The means where the research hypothesis is true. This is what we're, what we're comparing. And that's everything under this graph, okay? And you see that there's some overlap between those two curves. We set alpha. Oh, the effect size is the difference between the two means. And there's also another video on YouTube that I will link here as well that shows how a difference in effect size will affect the relationship between power as well. So this one we only have one effect size, but there is another video where you can see the difference, how we change effect size, and then we are able to change this relationship with power. Okay, so the cutoff value is where we set alpha. And alpha is everything under this red curve here, all this red area under the curve, and we're setting that on the comparison distribution. By us setting alpha, we're saying that everything to the right of the cutoff in the distribution of means, that right curve, would be we can reject the null. But by doing that, we have this area beta on that comparison, on our distribution of means, where we're going to make a type 2 error, okay? Any of that would be a type 2 error. There really is, you really are pregnant, but they're telling you you're not, okay? You're 8 months pregnant and they've told you you're not pregnant. We're in that type 2 error, that beta. And power is everything else in that distribution of means, okay? So power, the reason power is 1 minus beta, because the area under that curve is essentially 1, right? Because we're talking about percentages, so it's essentially 1. We subtract out the risk of that type 2 error, okay? And what we're left with is power, the ability to say that there's an effect when there is an effect, okay? And again, by setting this alpha level, we dictate beta and power. Again, there's another link. It's really short. I think it's like a minute, if that. It doesn't even have me talking, so you don't have to listen to me anymore. That shows how when we change the distance of these curves to each other, we change the effect size of these curves, that this relationship, power can be diminished, power can be increased, these sorts of things. See you in class.